Section 5.2, evaluate and graph polynomial functions. So a polynomial is a monomial or a sum of monomials. An example would be 3x squared plus x minus 5. A polynomial function is a polynomial that has all exponents that are whole numbers, meaning they are all positive, no fractions, no decimals, and all of the coefficients are real numbers. So there's no imaginaries like we had looked at last chapter. So an example of a polynomial function here. Parts of this polynomial function that you need to be able to identify are the lead coefficient, which is always the number that is the coefficient of the variable with the largest exponent. The degree of the function is always the largest exponent. And then the constant is always the term that does not have a variable. So it's just a number. So these polynomial functions can all be written in standard form. That means your terms are written in descending order of the exponents from left to right, meaning the largest exponent goes on the left, so it goes first. And as you move to the right, you go down in that exponent size. So an example here, notice we don't have an x squared term, so we just skip that term, and this would still be standard form. So some common polynomial functions that you're going to be expected to both know the name for and be able to tell me degree, lead coefficient, and what the graph looks like. So this table, more than likely, you're going to need to spend a little bit of time studying. So our first type of polynomial function is called a constant. That's where your polynomial is just equal to a number. So the degree of these is 0. There is no variable to have an exponent on. There is no such thing as a lead coefficient in a constant, so that's not applicable. And then graphs of constant functions are always horizontal lines. The next type is a linear function. We're pretty used to linear functions. These are always degree 1. If you have a linear function, it's not shown, but there is the variable, or the exponent, excuse me, of 1 on that variable. The lead coefficient here in this example is 5. But the lead coefficient for all of these tells us whether we have positive or negative slope. That's important because the graph of a linear function is always some form of line, diagonal line. Next is quadratic. So remember the name quadratic. That's when you have a function that is degree 2. Largest exponent is 2. The lead coefficient of this, actually let's skip to the graph. If we remember back to chapter 4, when we graphed these quadratics, we always had a parabola graph. And the lead coefficient told us which way that parabola opened. If it was positive, it opened up. If it was negative, it opened down. Next two we haven't seen before. First one being a cubic function. Degree is always 3, so the largest exponent in a cubic function is always 3. Jump over to the graph again. The graph looks a little bit like an S, some people say. Looks a little bit like the letter N, especially as we look at some of them in the future. The graph will still take this basic shape, but it'll start looking more like this. Okay, that's still a cubic graph. Now, the lead coefficient for a cubic graph, if it's positive, it'll open the way that I have these two examples drawn. If it's negative, it'll be the opposite. So if it's a negative lead coefficient, it will be coming down from the left as we go to the right. And if it's positive, it'll be going up from left to right. Then we have a quartic function. Degree of a quartic function is 4. Quartic functions graph take the shape of a W or an M, depending on whether the lead coefficient is positive or negative. If it's positive, it'll look like a W. If it's negative, it'll look like the M. It'll open down. The odd degrees, if you look at the linear and the cubic in the table, the ends of the graph always point opposite directions. Very important thing to remember. And for both the even degrees, the quadratic and the quartic, the ends always point the same direction. So if you ever have to sketch a graph, those two things definitely need to be shown in your graph. So first thing we're going to look at is deciding whether or not we have a function that is a polynomial function. If it is, we're going to put it in standard form, tell the degree, the type, and the lead coefficient. So for A, if we look at all the exponents, they are all real whole numbers, and all of the coefficients are real numbers. So this is yes, this is a polynomial function. If we put it into standard form, it would look like g of x equals pi x squared plus 7x minus square root of 3. Again, that means standard form means that you go from the biggest exponent on the left, working your way down to the constant would be the last term on the right. So now our degree is 2. So if I asked you to name that, you would need to tell me that it is a quadratic. And the lead coefficient is the pi. The example B, this would not be a polynomial function because the -1 exponent is not a whole number. Whole number means it has to be a positive value. The example in C is also not a polynomial function because the 2 to the x, sorry, this is a typo. Let's fix this. The 2 to the x does not have a variable base and a whole number exponent. They're flip-flopped. The variable has to be the base. The exponent has to be the whole number. So evaluating polynomial functions, there's 2 ways we're going to do this. The first way is what you're used to. It's called direct substitution. This just means that you are going to substitute the x value that you've been given into your polynomial function. So if we have x being 3, we plug 3 in for all of our variables. And if you just use your calculator to type all those numbers in, you'll find that you get 23. So your answer needs to be written in what's called function notation. F of 3 equals 23. The whole point is so that we can see what the input value was. So we plugged in the 3, and then the output value was that 23 that we got at the end. Okay, that's the one that you're used to. There's this other way called synthetic substitution. In order to use synthetic substitution, your polynomial needs to be in standard form, which we said earlier was largest exponent on the left, work your way down as you go to the right. So we have the function 2x to the fourth minus 5x cubed minus 4x plus 8. Maybe one thing that you notice about that function is that there's no x squared term. So it's very important when you use this synthetic substitution, you have to fill in 0 for any of the missing terms. So we really have a missing term here. It's that we would really have a 0x squared. So when you do synthetic substitution, you're going to set it up like this, these black lines here. You're going to make kind of a half box over here on the left. And inside of that box, you are going to put the x value that you're given. So we're given x equals 3. I put a positive 3 there. Then to the right of that box, I need to list all the coefficients. This is why it's important that you have your polynomial in standard form, which ours already was. These need to be in the right order. So all the coefficients, space them out a little bit. Notice I have the 0 in there for the 0x squared. So now what we do so the setup is done. What we do to actually use synthetic substitution. First thing we do is we take the very first coefficient and we pull it all the way down under the line. Make sure you leave some space because you're going to have to write some things above the line and below the line. So now, any number below the line, you're going to multiply by this x value you have in this little half box over here. So 2 times 3 is 6, and I write that underneath my next coefficient. So to go from there to there, I multiplied by 3. Then I add straight down. So -5 plus 6 is +1. Then I just kind of repeat that pattern. I go from there to there by multiplying by 3. 1 times 3 is 3. I add straight down. I get 3. Now I would have 9 here, because again, I'm multiplying this by 3. Then I'm going to add straight down. That would give me 5. Again, multiplying by 3, I get 15. And then I add straight down, and I get 23. This number, the last one, is your solution. So now we just have to write our final answer as f of 3 equaling 23. And you'll notice that's the same answer as the previous example. We did the exact same problem using the 2 different methods. You can see that they end up with the same solution. Synthetic substitution is a little bit nicer sometimes because you're dealing with much smaller numbers, so you don't have to maybe rely on a calculator. When you do your synthetic substitution, all these lines and arrows I have drawn in here, you do not need to draw those. I just put them in here for your notes so that you can see more of what's going on. So our next example, again, using synthetic substitution just to help us get used to this process. First thing, we'll have to make sure we have standard form for our function. So we do. If you look at the exponents, they are reducing by 1 as you move from left to right. The biggest one's on the left, constant all the way on the right. We also need to check, are there any terms that are missing? We go from x cubed to x squared to x to constant. So there's nothing missing in this one. We don't have to worry about putting any zeros in. So we start with our setup, make our little half box. In that half box, we are putting the number, the x value that we're given. So that's 2. Then to the right of that, we write our constants. So 5, 3, -1, and +7. Then we leave some space underneath, and then we draw our horizontal line. So now, go through the process. I'm not really sure why, but I always draw the arrow in just to show that myself that I'm dragging down the 5. If you don't put it there, it's not a big deal. So then to get numbers above the line, you have to multiply by what's in the box. So 5 times 2 is 10. Add straight down, 13. 2 times 13 is 26. Add straight down, you have 25. 2 times 25 is 50. Add straight down, and you have 57. So the answer to this problem, or what you get when you evaluate this polynomial function for x equals 2, is 57. You just have to write your answer, and it's done. Okay, now talking about end behavior when it comes to polynomial functions. End behavior is looked at, what is the graph doing as the x value approaches positive infinity, which is written like this, or negative infinity, which is written this way, so you don't have to write out the words. So we have to remember a little bit about some of the graphs we looked at earlier. Odd degree versus even degree, that's really the biggest thing. If you have an odd degree function, remember we wrote earlier that the ends of the graph point opposite directions. So just with a positive lead coefficient, that graph would take this shape. So from the left to the right, it's going up. There may be a hill and a valley in the middle. But then our end behavior I have written down here in the black as this graph itself is going down, so it's approaching negative infinity as x approaches negative infinity. So what that basically says is as I move further left on the graph, that blue graph would keep going down and down and down. And then the other part of it, there's always two parts to end behavior. The function is continuing to increase, so it's going towards positive infinity as x keeps getting bigger or goes to positive infinity itself. So then taking an odd degree and looking at the lead coefficient being negative, this graph that we have right up here would basically be flipped vertically, so it would look like this. Now the end behavior is flipped around as well. So the graph is approaching positive infinity, so it continues to go up as x continues to go down. So as you move further left on the graph, it keeps going up. And the graph would continue to go down as x continues to increase, so f of x approaches negative infinity as x approaches positive infinity. Then your even degree. Even degree looked like either that w or that m. If it's a lead coefficient that is positive, it looks like the w. So now this time, since we have a positive function graph, the two ends are going to point the same direction. So they're either each going to approach positive infinity or negative infinity. In this case, they're going up, so it's positive infinity. Doesn't matter if you're going to negative infinity going left or positive infinity going right. And then the lead coefficient being negative would flip the graph over, which would also take your end behavior and have it approach negative infinity as you continue to move left and negative infinity as you continue to move to the right. So one thing you're going to be asked to do with this is look at a graph and describe the degree and the lead coefficient of each of these graphs. So first thing you look at for the degree is the shape of the graph. Is the shape of the graph more of like that N shape, or is it more of the W shape? Well, this one is more of the N shape, so that tells us that this is odd. We're not looking for a number value, we're just looking for odd or even. And then the lead coefficient, since this graph is coming down left to right, yes, in the middle part you have some up and down, but overall coming down left to right tells us that our lead coefficient is negative. Okay, another big giveaway that you have an odd degree over here on the left is that the ends of the graph are pointing opposite directions. Graph on the right, the ends of the graph are pointing in the same direction, which tells us this is an even degree. And since it's opening down and those ends are pointing down, again, the lead coefficient would be negative. So being able to look at a graph and telling whether the degree is odd or even and the lead coefficient positive or negative is a skill you're going to have. And then finally, describing end behavior for a polynomial function. I'm not sure why these aren't written in here, but this would be as x approaches positive infinity, and this one is as x approaches positive infinity. So what you need to do for something like this, if you're supposed to describe end behavior, right, I suggest you sketch yourself a real quick graph. And to do that, you look kind of like with the graphs that we just looked at, you look at two things. You look at, is it an odd degree or an even degree? Is the lead coefficient positive or negative? So A, we have an odd degree with a negative lead coefficient. We have to be able to tell that our graph would then look something like this. It's not a perfect graph by any means, but that's the general shape, and that's all we really need. So describe the end behavior. If that's our graph, as we continue to move left on that graph, where is that graph going? It's continuing to go up. So we would have positive infinity as x approaches negative infinity. And if we were to continue to move to the right, that graph would continue to go down. So that's negative infinity as x approaches positive infinity. Example in B, that is an even degree with a positive lead coefficient. So our graph would look something like this. Again, just general shape, not worried about being specific at all. And then if this helps, put it kind of on a random x and y axis, helps you see your x a little bit better potentially. As you move left on this graph, that graph would continue to go up, so that end behavior would be going towards positive infinity. As you move to the right on this graph, that end behavior would continue to go up. That would be, again, positive infinity. So if you need to hear anything again, go ahead and go back in the video. Use the video while you are working on your homework. And that's all we've got.